Hey guys, today we're going to be talking about fluid mechanics by me, Jan Philippe Ang. So let's get right. A tall cylinder with a cross-sectional area of 10 centimeters squared is partially filled with mercury. The surface of the mercury is 6 centimeters above the bottom of the cylinder. Water is slowly poured in on top of the mercury and the fluids don't mix. What volume of water must be added to the cylinder to double the gauge pressure at the bottom of the cylinder? So here's a diagram, and we're looking for the volume of water needed to double the pressure. So we have an area of 10 cubic centimeters and a height of 6 centimeters, and we are looking to add water. So the formula is density times gravity times height, and the density is 13.6 times 10 raised to 3 for mercury. And then you multiply everything out and you get 7,996.8 pascals. And you multiply this by 2 because we're doubling it. So 15,993.6 pascals will equate the two pressures. So all you have to do is isolate your height. So you have 15,993.6 minus the pressure of the mercury divided by density of water times gravity. Multiply everything out, divide everything, and you get 0.816 meters. Now we look for our radius. So our radius is simply 0.178. You could do simple algebra with that. And now we look for volume. Volume would be your height times pi times r squared, and you will get 0.816 times pi times 0.178 squared, and you will get your volume as 0.0816 cubic meters of water is required to double your gauge pressure. Alright, so for our next problem, we're going to look at something more difficult. Alright? So if you have any questions about this problem, feel free to send me an email. A narrow U-shaped glass tube with open ends is filled with 25 centimeters of oil with a specific gravity of 0.8 and 25 centimeters of water on opposite sides with a barrier separating the liquids. Assume that two liquids do not mix. Find the final heights of the columns of liquid in each side of the tube after the barrier is removed. For the following cases, arrive at your answer by simple physical reasoning, not by calculations. What would be the height on each side if the oil and water had equal densities, and what would the heights be if the oil's density were much less than that of water? So we have two parts to this question, and let's get into our required and given. So this is a diagram, and all we're looking for is height of oil and water. So once again, we use density times gravity times height, and you equate those because they're at open ends. And we denote our height as 25 minus h and 25 plus h. And the gravities cancel out, so you get the equation of 25 minus h equals 20 plus 0.8 h. So we can find our height difference to be 2.78, and we add and subtract respectively. So we get 22.22 centimeters and 27.78 centimeters for water and oil respectively. They would remain the same height if they were the same density, and the height difference would be much higher if oil were less dense, because it is already less dense and it is higher than water. So if it were lessened, the height would increase. So that is it for that problem. So just to clarify, that's density of water equals density of oil. Alright, so that's that. A piece of wood is 0.57 meters long, 0.25 meters wide, and 0.076 meters thick. Its density is 700 kilograms per cubic meter. What volume of lead must be fastened underneath it to sink the wood in calm water so that its top is just even with the water level? What is the mass of this volume of lead? So here's a diagram, and we're looking for the volume and mass of lead. to be attached to the piece of wood so that it would just be on the surface. So we know that the buoyant force is equal to the weight because it is on the surface of the water. And you get density of water times volume of lead times gravity equals density of water times volume of the block of wood times gravity equals the density of the block times volume of lead times gravity plus density of the block times volume of block times gravity. That's your buoyant force equals your weight. So all you have to do here is isolate your VL and all on one side and your VB on the other side so that you can factor them out. So you get VL times density of water times density of minus density of lead equals VB times density of your block minus density of water. Then you isolate your VL because you already have your VB, and once you multiply everything out, you get 3.15 times 10 raised to the negative 4 cubic meters. Then we look for our mass. So we know that our mass is density times volume. So you get 11.3 times 10 to the third power times 3.15 times 10 to the negative fourth power, and you will get a mass of 4.47 times 10 to the negative 6 kilogram. So it makes sense because lead is pretty heavy. It's very dense. Wood is not as dense. So you don't need that much of that big of an amount of lead to sink that amount of wood, considering it wasn't very big to begin with. So thank you guys for watching. I hope you guys learned something, and I hope you come back next time. Goodbye.